Okay, so this is a 468 class, but people taking 467 should attend unless you're absolutely bored out of your mind with the concepts. Let's start with questions because this should be a questions-driven class. I don't know where I'm supposed to put this, so I'll just put it there. Okay, so what would you like to talk about? Hint for 725. Okay, let's go to 725. Right. So let's see. We want to use Bessel's equation. Which is whoops, it disappeared. Hold on. LU is minus x u prime prime plus n squared over x u equals lambda xu. So that's, let me just flip back here too. So if I've copied it correctly, that's Bessel's equation. And what we want to do is we want to use the boundary conditions that u of 0 is 0 and u of 1 is 0 for n greater than 0. So I guess we're strictly for n greater than 0. And we want to show that lambda is positive. Right. Well, let's see. I don't frankly immediately see that answer to that. So let me look at the solutions that I wrote up for this problem a couple of, well, actually probably several years ago. So where, whoops. I'm still moving the mouse. Okay. So, so basically we just, right, we multiply Bessel's equation by u and integrate from, yeah, basically the idea is to mimic the stuff that you learned in an earlier section in this chapter. So let's just go to the chapter on eigenfunctions, eigenvalues of self-adjoint systems. And I think the best place to look is here. You see this energy eigenvalue. Remember, the eigenvalues are given by this ratio. So you just have to compute this ratio for a given self-adjoint system. And what you know is the denominator is positive, and you then have to proceed from there. Now, I'm afraid I've done too much of the problem for you, but the thing is you study section 7.37, this section here, and in particular this ratio and the fact that lambda is the ratio of E of U over N of U, and just compute what that is. All you need to know is the sign of it. All right, let's go to a next question. As I've said, I'm not great at listening, and I'm even worse at reading minds. So I need you guys to suggest to either ask a question or to ask me to explain something or to do something. Do you have any questions about the applications to cosmology here? So let's see. I don't see any more questions. Well, do you want me to just plow on through Bessel functions? As I said, I'm terrible at reading minds. So why don't we just do that? And then worst comes to worst, you can see you'll see these things done twice. So the Bessel functions are defined for any integer n greater than or equal to 0 by this series. And the first term in the series, obviously these terms drop off rapidly. If z is less than 1, then these terms drop off, both because of the n squared in the denominator and the factorials. These are actually factorials, so the convergence is very rapid. And then you have powers of z. And so for small z, the biggest term here is just the first term, 1. And you get that Zn is just z to the n over 2 to the n factorial. And the alternating signs, minus, plus, minus, mean that the thing is like it's like a wave. And in fact, there's an approximation that I just quoted, didn't derive, namely that it's basically root 2 over pi z times a cosine, and the cosine is z minus n pi over 2 minus pi over 4. And then there are correction terms, and the correction terms are 1 over z to the 3 halves. And of course, that means that this approximation is really good for large z. This thing is power series in z squared. It's power series in z, But because of the factorials, it converges very, very well. And so the Bessel functions are all entire functions, and they obey, as I said, Bessel's equation. And you can show that they obey Bessel's equation by taking this series and plugging it into this differential equation. So that's one way to proceed here. In other words, you basically take this series and substitute in there, and you can see that you can verify explicitly that they satisfy. These are the Bessel functions. First 5 Bessel functions, and you can see their waves. Jn of 0 is 0 unless n equals 0, and then J0 of 0 is 1. It turns out that the places where the Bessel functions cross the origin, that is to say this line j equal to 0 here and j equals 0 there, these are the zeros or roots of the Bessel function. And as I mentioned to you in an earlier lecture, during the Second World War, they were actually state secrets of the British Empire. Of course, I imagine the Germans had approximate values and might even have had better values than the English. I don't know. Anyway, there's a generating function for the Bessel functions, and it's e to the z over 2 times u minus 1 over u, and that gives you u to the n jn of z summed over n. And one can also derive an integral representation for the Bessel functions. This is kind of a mystical expression, I find. We've got an integral over theta, and the theta appears simply in the second term, but in the first term of the cosine, it's z, which is this z, times the sine of theta. So this is a very strange expression. And it turns out that it's actually used in certain physical cases. I think Glauer used it to do part of his theory of scattering of composite objects. For n equals 0, the thing simplifies somewhat, and it's just cosine of z sine theta, and it turns out that you can rewrite that in either of these forms. And since you're integrating from 0 to 2 pi, you can change cosine into sine. And these integrals tell us that j of 0 is 0. Let's see if is that obvious. If we set z equal to 0, we're just integrating from, wait, where is n? Right, this is j of 0. So setting z equals 0, we're just integrating 1 from 0 to 2 pi. That's 2 pi. The 2 pi's cancel, and we get j of 0 is equal to 1. To show that jn of 0 is 0, well, you have to think a little harder and look at this expression up here. I think actually if you put z equal to 0 and look at this, and that, you can figure that out. Anyway, suppose we differentiate the generating function, this one, with respect to u. Then we get a recursion relation. Here's another, taking the z derivative of similar reasoning, but then taking the z derivative, we get this. So we have 2 recursion relations. notice that the original expression here was a sum involving factorials. Well, you remember there's a relationship, namely that z factorial is equal to gamma of, and I think it's z plus 1. I'm guessing it's either z plus 1 or z minus 1. I can never remember that. So let's see what the answer is. Let's see if that gives us the right. Z factorial is z plus 1, gamma of z plus 1, right. So you can convert one of those expressions there. M obviously is summed over integers, but the other one was m plus nu factorial. So in other words, the expression was j, let me do it slowly in 2 steps. Jm of, no, not Jm, that was dumb. Hold on. Earth to all right, so now let's go. Oh, damn it. I'll probably learn how to use this iPad and Apple Pencil after the pandemic is over. Jn of z then is z over 2 to the n, sum on m from 0 to infinity, and it's minus 1 to the m, and we're dividing by m factorial, m plus n factorial, and then z over 2 to the 2m. Now, why we've got this expression with z and not z over 2, I don't know, but that's the tradition. That's the way Bessel did it, or at least that's the way his followers did it. But now we can use this expression here. Let me go to green. We can use this expression to substitute for this term here and change, let n go to nu, where nu is in fact just complex. And we just have to make sure that it's not a value that screws up the gamma function. And so what we then get is j nu of z. Well, it's the formula that you see in front of you, so it's written better than, well, I might as well continue this. Z over 2 to the nu, sum on m, minus 1 to the m, divided by m factorial. And now this would be gamma of m plus nu plus 1 times z over 2 to the 2m. So, and that's cos m equals 0 to infinity. So that's extending this to basically all complex nu. And so I said here non-integral values, but in fact, the gamma function is an entire, well, it's not entire, but it's good everywhere except at 0 and the negative integers. So as long as nu has an imaginary part, equation 1010 is just fine. And if the real part of n is positive, it's fine. If the real part of n is a fraction, or at least is not a negative integer. If it's a negative integer, or we're in trouble. But if it's not a negative integer, if nu is not a negative integer, this is golden. And so that's an enormous extent. This is an example of analytic continuation. And in fact, when I mentioned analytic continuation back in the chapters on the gamma function and on functions of a complex variable, I think I mentioned that the gamma function was the archetypical or the best example of analytic continuation. Anyway, the self-adjoint form of Bessel's function, if we set z equal to kx, then we get the equation in a more useful form, because in this more useful form, you see, you've got an extra parameter here, so that when you can connect this with a physics problem or an engineering problem, because you've got this extra parameter here. And that's why typically when you see solutions in physics of involving Bessel functions, you see Jn of k rho. Rho is x, because the reason to switch from x to rho is that you go to cylindrical coordinates and you use the Bessel function as the radial function in cylindrical coordinates. Let's see, do we have a question here? Because you probably don't want me to plow on with Bessel functions. Working through example 8.2. All right, well, we can jump to 8.2 right now, remembering that we got to this far. So let's see about 8.2. Example. I'm not seeing any examples here. Oh, there's 8.1, 8.2. Okay. Yeah, this was a good choice of something to ask me about. Very timely question. So if we multiply Bessel's equation, I guess, by z or z squared, we get this equation here. And the differential operator then you can think of as z squared, second derivative, z first derivative, plus z squared, and then this is the eigenvalue term. And we can think of c as minus L squared. So what we're doing here is we're mimicking, we're working through this integral transformation business. Remember, what you do is you write the differential equation in this form, and then you say that, well, you don't know what u is, but you think you can represent it as k times z of k of z and w, v of w, integrated along some contour in the complex w plane. And then if that's u, then you know that you should have lk. Yet let L acting on u is lk. And then cu would be ck. And so taking this equation, or to put it differently, substitute this into that, and we get this equation. And so now what you want to do is you want to find an operator m, so that when m acts on k, you get L acting on k. And you want m acting on k with w derivatives. You want that to be L acting on k. And of course, L has z derivatives. That's what, that's the original differential equation here with z derivatives. So you invent such an m, and if you can find such an m, then you substitute for lk, you just write mk. And now this whole thing is something involving m derivatives here and an integral of k. And if k is suitably simple, then you can integrate by parts. And so that's the scoop. Now over here, what we're going to do is figure out we're going to, well, actually, I think I got the cart before the horse here. because the first thing you do is you first choose K, and over here, I chose M first and then looked for K. So I interchanged M and K, I think, by mistake. Yeah, well, all right, well, let's just go through it anyway. Yeah, I think the labels here, I'm going to have to redo this, but basically the idea here is that you have well, actually, you know what? I think maybe I've screwed this up. I'm going to have to think about this because, as I say, I think that the first thing you do is you pick a the notation here is that you first pick a K so that you can write U this way. And let's see if I'm, all right, let's say that we pick this as K. Okay, and then we choose, so I've sort of got things backwards. We first pick K equal to this, and then we need to find an M, and we decide that M is D2 dW squared. So, and the idea is that D2 dW squared on K should give L on K. And so what is the situation here? It would be this, so M is minus D by dW squared. And so we have M on K is L on K. L on K is equal to this. And if we set K equal to that, then what we've got is that we want this equation to be satisfied. And this minus sign has canceled that minus sign. So then we have the second derivative, W derivative of K plus lambda squared K integrated on V should be 0. And now what you can do is you can integrate by parts. Since this is a second W derivative, you just write this as the first W derivative of this product. And when the WX on V, that cancels the first term. When the WX on K, we get this term. So that's how this equation follows from that one. And now we integrate by parts yet another term, and we get this expression. And so at this point, we simply want this to vanish at this quantity within the parentheses to vanish at both ends of the contour. And if we arrange that, then all we need is that V double prime plus lambda squared V should vanish, where these are W derivatives. And so V is some function of W that only satisfies this. Well, this is just the harmonic equation. So any exponential basically satisfies this equation. And we then choose the contour so that these boundary terms vanish, so that this vanishes at both ends. And so that gives us this expression. So now we've written the solutions of the Bessel function in this way, just as long as the contour is correct. And so at that point, we decide, well, suppose the real part of Z is positive. Okay, if the real part of Z is positive, then if W, remember the contours that we had, whoa, I've got to fix that, so undo. Also, I think all right. So the contours we were talking about for this problem were ones where we go from very large, very high, or very low in the complex W plane. So if W then is essentially I times infinity, and lambda we're thinking of as, well, let's see. What we've got here is, oh, this is, you see, this is huge here because this is sine of W is, you see, this is, all right, this is a little bit complicated to evaluate actually, but hold on, let me go to black. So what we've got here is e to the minus iz sine W. Well, sine is 1 over 2i e to the iw minus e to the minus iw. Okay, and then plus I lambda w. Well, the real dynamite is this top equation here. If we cancel the i's, we get e to the minus z over 2 times e to the iw minus e to the minus iw plus I lambda w. So now if we're up at where W is I, if W is, oh gosh, all right, I screwed that up. Let's just, if I infinity is W, so I've written the equation backwards, then what do we have? We have e to the minus z over 2 times e to the minus infinity minus e to the plus infinity plus I lambda w. Well, this thing is trivial. The real dynamite term here is, this thing is essentially 0. This thing is essentially minus infinity. This is infinity, and we have a minus infinity, and we have actually an e to the plus there. Did I lose a sign? What did I take z to be? I took z to be real z is positive. So I've got sine of w is e to the iw minus e to the minus iw, e to the minus iw times, so that's huge. Somehow I've got this thing not as vanishing, but I've got it as huge. So oh, damn it, you can't see the board. Ugh, I'm sorry, gosh. Listen, I think it's really important when I'm doing something wrong for you guys to speak, because I don't always glance at the chat function. So if I'm doing something if I'm, for example, covering up the iPad, just shout it out. Don't wait for me to discover it on the chat board. And I'm just wondering if I somehow got the sign wrong in the exponent there. We've got a pi so W is minus pi. Oh. So these pi's I've been ignoring because I've thought that they were not doing that much. So, okay, so it's really good that I did this example in detail because you see, it's not really trivial. I went too fast here. So what we want to look at here is the term that you see W, what we have here is e to the minus z over 2 times e to the I. And here W is, let me move this over so that it doesn't, okay. So W is minus pi plus I infinity. So this thing is e to the I minus pi plus I infinity minus e to the minus I minus pi plus I infinity. And then plus a relatively negligible term. Now the point is these minus pi's fix the minus sign that I was seeing. So e to the minus I pi and e to the I pi are both minus 1. So this is really e to the z over 2 times e to the minus infinity minus e to the plus infinity, and then plus I lambda w, not infinity, w. Well, this is e to the minus e to the z over 2 time. So this is effective. I mean, this is huge because you see, this is e to the infinity, a minus sign. We're saying real part of z is positive. So for real z greater than 0, in other words, z is equal to some x plus I, y, and x is greater than 0, then this thing is e to the minus infinity, e to the plus infinity. So this is really super 0. Okay, so that's what I've gone through then in a little bit of detail here is one of the contours, and the contour here for C1, it goes up to minus pi plus I infinity in the W plane. This is the W plane. And where does it start? Starts from minus infinity, right? Minus infinity, minus I infinity. So the deal is that when we flip the sign here in the exponent of e to the iw, we're going from you see, it's minus pi plus iw is what this is. And then if we switch simply to w equals minus I infinity, we don't need the pi and we still get 0. Okay, so that's some of that. Now there was a question about 734. Let me try to get to, oh wait, 734. Universe of radiation. So you're supposed to derive these two equations, if I've got that Right. So let me just see what we're talking about here. I think this is a pretty easy problem. Right. So what you have to do here for a universe of radiation, well, that's this curve down here. And what you do, and you're in a Friedman-Walker universe, so you just take this equation here, and I think I said set k equal to 0, so you blow away this term. Then you've got things that are pretty simple. And so the question is, what's rho 0? Well, rho 0 is the matter density, or the mass density. And let me see what the notation that I used was. I actually kept L in the solution. Do we need to keep L in the solution? Universe of radiation. Let me see here. Yeah, I kept L. All right, so you've got to keep L in the solution. So you have to, the easier one to integrate is this equation here, because it just involves a first derivative. So you take a square root of that and you get an equation for A dot. And now you need an equation for rho 0. But what, let's see, I'm looking at the solution here. Oh, yeah, all right. So let's just to make everything a little bit simple, let's set r to the fourth, sorry. Set r to the fourth equal to 32 pi Newton's constant, rho 0 over 3. And now what is rho 0 here? Well, rho 0 is the energy density due to radiation now. And so let me jump back to the Friedman equations here. You see, we've already put in the W dependence. So for radiation, what is W? If it's a cosmological constant, W is -1. Let's see, for radiation, W is a third. So you go up here and you set so let's, W is a third. Oh, sorry, I was here. So you just set W equal to a third here. So this is 4/3. So this is A to the -4. And rho then is the present value of the radiation. And so let's see. Yeah, right. So I said set this r squared equal to that. And then once so in other words, I didn't bother to actually evaluate what rho 0 is, but it's a constant. Once you set W equal to 1/3, then the Friedman equations take this simple form, and then you just have to integrate this. And that is pretty simple because it means that you have A dot is equal to some constant, call it Q over A. And so that's dA dt. And so that gives you dt is equal to 1 over Q dA over A. And so that's T minus some constant. I would say T0, but the astronomers take T0 to be the present time. So I'll just say T minus T1 is 1 over Q. This is the log of A over A1. And now you invert this equation. And then sorry, we've got, let's see, I left out, all right, I went too fast here. I left out the K term. So you've got to do it a little bit more carefully because you've got that. So this is for K equals 0. For K equals plus or minus 1, you take the square root of this equation. And so again, you have A dot equals something, but now it's a square root of, say, B over A squared minus some constant, well, it's C squared K over L squared. And now you have to just integrate this, and that's dA over the square root is integral dt. And so you do this integral. And that's B over A squared minus C squared K over L squared. So you just do this integral and you should get these solutions. So let's see, as I was going over this, I noticed that there's rather a nice expression here involving the Bessel functions, the J1. I wondered, did I assign one of these as a homework problem? Right. Well, why don't I instead of assigning it as a homework problem, why don't I grab it here and sort of do it for you. But I mean, if somebody has a question, quick. Oh God, we're out of time. Okay, so one question here, would you? All right, so let's say that I will do one of these delta function examples, and it was basically problem 28. I'll do problem 28 in class at the start of class tomorrow because that one's about Bessel functions. We're talking about Bessel functions, and it tells you once again what the completeness of eigenfunctions of self-adjoint differential systems, why they're complete and what the completeness means. We'll have to go a little bit further. I think what we should do is we should first finish cylindrical Bessel functions, capital J. In other words, we'll go here. Bessel functions of the first kind. So we've gotten a certain distance in. We basically go to here and we could maybe stop here and do the example, or we could go up to basically, well, all of this we need to do, but we don't need to do Bessel functions of the second kind tomorrow. Anyway, we'll fit it in and do it tomorrow. All right, sorry for all the confusion today. Have a nice weekend. Oh, it's not a weekend yet. I'll see you tomorrow at 5:30. Stay warm. It's been really cold the last few days. So I'll stop sharing.
Thank you. Have a good night.
Yeah, you too. Thanks. So.